What is on
hard to tell. Actually, probably, well, I don't know.
Is it still to come, or?
I'll refrain from comment. Today is the 17th.
Is this stuff branching off of Chapter 3 stuff, too?
This stuff incorporates Chapter 3 stuff. This is really ugly math. This and Chapter 5 are the ugliest math we do. So, but having done Chapter 3, you will be better prepared. Woo! Okay, so this stuff builds on things you learned in physical science. You all know that mass times acceleration equals what? F equals ma. So we even have science club shirts that say, "May the F equals ma be with you." Oh yeah, may the may the ma be with you. So this is not, you know, the early part of this is pretty tame. At its root, force is just an object interacting with its environment in some way. I'm going to not knock over my coffee. So force causes acceleration. When you put a force onto an object, and it's not balanced by something else, when there is some net force on an object, it changes its velocity. Does this rock, with regard to the Earth, since we're talking about frames of reference, does this rock have any velocity right now? Does it now? Okay, so a force acted on it. Unless we see a force acting on, and if something is moving, a force is acting on it. Okay, if it's changing its velocity. I think.
You know, I've been trying with this before.
Okay, physical science was a long time ago. So, oh, okay. So, the Newton, shown as capital N, never lowercase n, always capital N. That is the unit, that's the SI unit for force. You will use newtons until you are so stinking sick of them, you will run screaming, or you will fall so in love with them that you will name your first child Newton, or your next dog, or whatever. Actually, that'd be a great name for a dog. Okay, so 1 Newton is the amount of force that it takes to get 1 kilogram of mass to accelerate at 1 meter per second. So we can do dimensional analysis. Yay! I knew you've been missing it. You've been waiting for it. Yes, I can. So 1 Newton is what it takes to get 1 kilogram of mass to accelerate at 1 meter per second squared. Now, let me get you a kilogram mass. Kilogram mass, we put it on a rolling cart. There's our 1 kilogram mass on a rolling cart. Hey, let's get a rolling cart. Okay. I can't read anything on my screen. So what force is acting on you? Gravity. Are you touching the Earth at that point when you're at the top of your flight? No, you're not. But yet gravity is acting on you.
So gravity is a distance force.
Gravity is a non-contact force. It is a field force. Field forces are the ones that don't require physical contact. So gravity is one of the field forces. Electrical fields are another force, and so are one other kind of field. Can you think of what it is? Magnetic fields, right. You have electromagnetic forces that act at a distance. So those are your field forces. Contact forces, this is really important to note. When you push something, when you throw something, at the moment it leaves your hand, are you still acting on it? No. Your action on it is over. This is like the kick, flick, and push problems. You push it off the cliff, you kick it off the table, you do whatever. The minute that there is no longer contact, there is no action on that object. The only action at that point is gravity. And that's what we did with the kick, flick, and push. You know, and the angled lunge. They're falling under only the influence of gravity. Okay, so force is a vector, you know that. It has a magnitude and a direction. We can have multiple forces acting on things. We can do vector resolution. Yay! Sorry. It's represented graphically, just like any other vector is. And we're going to start to get into, by the end of today, you'll be practicing representing force graphically. We don't typically solve force vectors graphically. It's a little bit too tough to do, but they're really helpful. They're really helpful. And force is always shown with a line with an arrow indicating the direction of the force. And those typically are labeled. So, you know, in a situation where we have multiple forces, that might be force 1. And force is always capital F. And we're going to get into how to represent forces. 2 examples. Name me an object. Who do I seldom hear from? Ashley, name me an object. A pencil. Okay. There we go. There's our pencil. Did you know I was going to draw the object you named? Yeah. Okay. Okay, so we've got our pencil here. Man, you picked a really hard one for me, Ashley. Trying to kill me, kid.
Pick one of those really big pencils.
Well, no, because what's going to happen next is what's interacting with the pencil. Somebody with 3 fingers. Okay, I made 4 fingers, but there. That's as good as it's going to get. This is...
Cartoon.
Yes, it's definitely cartoon character-esque.
Looks like they got like.
Looks like their skin is peeled back.
Okay, so we have a car hitting a wall. What are all the forces in this situation? Okay, well wait, the car is exerting a force on the wall, and so we would show that. Now, a few quick notes about representing forces. I said we show forces with a line and an arrow. We show a force that is acting on an object as if it originates from the center of that object. So if we have a force that is acting on the wall, and I'm going to do all these lines in red, then the line extends from the center of the wall. No, it's not. The line extends from the center of the wall. That's the force that the car is exerting on the wall, right? Is the wall exerting a force on the car?
Yes.
Yes. In what direction is that pointing? Yeah. So that line would be here.
From the middle of the car?
From the middle of the car.
Wait, why? I'm confused.
Yeah.
Oh.
Well, that's usual at this point. They are opposite forces. And we're going to talk about force pairs, but suffice to say for now, and we'll get into more detail with this when we do force pairs, the force on the car is backwards. The force on the car is backwards. That force on the car is what's stopping it. The wall is stopping the car. The car was moving, and please note that I do not put that line connected to the car in any way. The car had some velocity this way, and it's stopping because there's a force that's acting against that velocity. Now, I know, it's okay. It's a little bit weird at first. It'll get better. We would label these forces.
So you just like put like the force, like the thing that's being acted on.
The force,
The way,
yes,
like,
the way the force is act in the middle of that object, right? It's going to get easier when we do free body diagrams. So this is the force of the car on the wall. This is the force of the wall on the car. So we do a lot of labeling. Are those the only forces acting on this thing? No. Good heavens, no. Now I'm going to put in more forces than we've talked about yet, and it's just to illustrate how ugly this gets and how fast. So we know that gravity is acting on the car. We know that the road is exerting an upward force on the car, or the car would be plunging towards the center of the earth. We probably have some other forces that I'm not even accounting for. And we would label all these. So this would be force of gravity on the car. I am.
I was really kidding.
It's not
It looked
there.
like it.
Everything from the gravity is said, isn't it?
Oh.
This is not good. Here we have force of the road on the car. The road is exerting an upward force. There's a name for that, but you don't know it yet. You won't know that until we get back from break. So there are a whole bunch of forces. Is there a gravitational force on the wall? Yeah, there is. So there's, whoops, that's not the thing I wanted. That's the thing I wanted. There's a force of gravity on the wall. Is there a force of the earth pushing up on the wall? You betcha. This gets real ugly real fast. I don't like it either. Which is why we're going to do free body diagrams. So this is just to show you that a force diagram is going to show every single force in a situation. You know, if there's a butterfly landing on that car, the force of the butterfly pushing on the force of the car pushing on the butterfly, the force of the passengers in the car with their butts on the seats, the force of the seats up on the butts of the passengers. It looks like a porcupine when you're done. It's awful. To simplify that whole thing, we do what is called a free body diagram. And we'll do a free body diagram on this page. I will pop that same slide back in if I can find it. There we go. So a free body diagram takes one object. So we could take the car. Whoops, let me draw the car in black again.
Wait, are we still on this slide or the next?
It's still the same slide. I just went to a new page. So a free body diagram isolates one object. And with that one object, we draw just the forces acting on that object, and we don't draw anything else. So we have this car. We don't draw the weight of the occupant. We don't draw the occupants. We don't draw the butterfly. We don't draw the wall. We only draw, so same situation, car running into a wall. We would put the force that the wall is exerting on the car, still coming from the center of the car. And I'm going to draw in the velocity of the car. So there was a velocity of the car that way. We would still label everything. So this is force of the wall on the car. We would still have a force of gravity on the car. And force of gravity is typically F sub G. We use a lot of F sub this, F sub that, just little subscripts to indicate what the force is from. We would still have a force of the road acting upward on the car. Yeah, there's a little bit of a delay there. Look, kids, no hands. And that's all we do. So free bodies are nice. They simplify the process tremendously.
What about the force of the
Yeah,
car?
what about the wall?
Is it on the car? Is it a force that's acting on the car? No. And in a free body diagram, we don't show it. In a free body diagram, we pick one object and we only concern ourselves with the forces on that object. Make sense?
You still need to draw the wall to like see
Nope.
if there's a wall.
Nope. 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 That's exactly the question I want to ask you. Ask though. Like, don't we draw this? Don't we do this? No.
What about the butterfly?
No butterflies. No people in the car. No nothing.
Isn't it the force?
We make it really simple. We make it really, really simple. It's a gross oversimplification, which is kind of our specialty in physics. Okay, so when you draw a free body diagram, we draw the object in isolation. That means we don't draw the wall, we don't draw the butterfly, we don't draw the people in the car, we just draw the object. And we sort of approximate the shape more as a mental cue to ourselves than anything else. So honestly, in free body diagrams, we do a lot of this. Okay, there's our object. You know, if it's a person, you might do something like that. There's our person. You know, we do these very sort of approximate blobs. Sometimes our blob is a little circle. You know, for cars, I do generally, I do something like this as a reminder, like, hey, that's a car. But we really minimize the level of detail unless we're kind of being cute about what we put into the object. Then we draw and label each force that's acting on the object. And to do that, like I said, they always start from the center of the object. Are you familiar with the term center of mass or center of gravity? If you have a high center of gravity, you're top heavy. If you have a low center of gravity, you're bottom heavy. For most humans, center of gravity is somewhere about here. And that's why there's the belt buckle rule on ladders. Do you know the belt buckle rule on ladders? When you're on a ladder, there are two rails going up. I'll draw it. You want to keep your belt buckle, or your belly button, or whatever, between those two rails, because that's your center of gravity. So as long as your center of gravity is still between those two rails, more of your gravity is on the ladder, you're less likely to do something stupid and get a Darwin Award for it, basically. So, center of gravity. So that's why we draw forces as if they are acting from the center of the object. So let me get rid of some of my little fake objects here. No, didn't do what I wanted it to. Cut. Okay. So we'll use this as our object. And if possible, we typically draw them hollow because it's easier to see where the forces originate. When we're doing this, it's really useful to color code if you are a color coder kind of person. We label the forces. So if we have this box, if we're looking at this object, whatever it is, from a top view, we're looking down on it. And we have 4 different people pushing on it. We'll recreate this in the hallway in third period. Let's say we've got Jack, Josh, David, and Brittany pushing on this box. Actually, let's just do this. Okay, recording now. So we've got our folks pushing on the box, they're pushing on the object, and those are the sides they're on. So let me ask you this. The force that Brittany is exerting on that box, which way on this diagram here is that force line going to extend? Upwards. Okay. So the force that Brittany is exerting, this is the free body diagram, yeah, is that. And actually, I'm going to get rid of the names now. So we know we've got Brittany and Josh on opposite sides. Okay, so how would we label that force? Well, we would label it F of Brittany. And we very often at this point, because we know they're all acting on the chair. So we no longer really have to say the force of Brittany on the chair. Well, there's nothing else shown here that's having a force exerted on it. So that is the force of Brittany on the chair. Where would we exert the force of Josh? Down. Now this is where the color coding does come in handy when we start to do calculations with this. And we would label this, and this would be force Josh. Where is the force? So that's Jack and David. We've got those memorized. Okay, where is the force of Jack going to be? What direction? Yeah. And we would label it. So that's force Jack.
Take that.
Yeah, well, you know, it's as good as it's going to get. And we've got one last force. We've got force of Josh. Where's that going to be?
Force of David.
Oh, force of David, I'm sorry. Be over this way. Okay. Now, I didn't draw these perfectly. At the point when they were all pushing but the chair wasn't moving, all 4 of those lines should be the exact same size because the forces are balanced. It's not moving. Right now, at this point, and I'm not going to count it or go down to scale, It looks to me at a quick examination like the force of David and Jack is about equal, and the force of Brittany and Josh is about equal. So that would also be the chair not moving. But David and Josh are exerting a little bit less force than or David and Jack are exerting less force than Brittany and David. I apologize, that's supposed to be off.
Yeah.
Take it, yeah.
No, I can't. It's an appliance. I'm having multiple appliance issues. Like your water.
Was it just like a
Hot water heater and dryer simultaneously. It's delightful. So I'm getting phone calls. My apologies. Pardon? True. You can always hang things to dry. Okay. Oh gosh, that was. Okay, so we've got our force diagram, and I'll probably do a force diagram tutorial, free body diagram tutorial, and plop that up there in place of this. So the big things are making sure they originate at the center, labeling them. Now, if we know the magnitude of these forces, we want to label them. You know, if this is 10 newtons and this is 10 newtons, we want to label them as such. Sometimes we don't know the magnitude of the forces. Sometimes we're finding out the magnitude of the forces. Whoops. Undo. We'll say that these are each 15 newtons. Or maybe we say that, you know, we're working to figure out the force of Josh. So those are the things you need to include.